Now let's find the induced electric field outside of the solenoid. Bet you weren't expecting to find electric field out here, given that we've got a changing magnetic field only inside the solenoid. But Faraday's law will force us to conclude that the changing B field in here will actually create an induced E field out here, everywhere out here. Okay, so step one, draw a Faradayan loop located at the location where we want to find the E field. So at some little r greater than big R, we will draw a circular loop. Choose our ds and our dA to agree. Once again, I want dA out of the page so that it is parallel with the magnetic field. And in that case, by right-hand rule, if my thumb is the dA out of the page, then the ds's must be curling counterclockwise. So our ds's point like that around this Faradayan loop. Next step, compute the magnetic flux through our loop. So the flux through the open surface bounded by our closed loop. Okay, magnetic flux will in general be a function of time because we're integrating b dot dA. This is an open surface integral over this surface, and b here is a function of time. All right, so I can break this up into two integrals. The integral over the part of the surface that's contained inside the solenoid, plus the part that's outside the solenoid. That would be this region here outside the solenoid, that area. Okay, well, outside the solenoid, there is no magnetic field. So that part's zero. We only have to integrate BdA over this area where there actually is magnetic field. So we see that since B and dA are in the same direction and B is uniform across this surface, this integral will just become the magnitude of B times the area of this surface where the B is located. Not the whole area bounded by our Faradayan loop, but just the portion of that area where B field is actually penetrating through the surface. So this term here will just become our magnetic field strength, which is a function of time, times the area pi big R squared. Not little r, but big R, just the area of the sort of the mouth of the solenoid where there is B field. No flux through this area out here where there is no B field. Okay, that was the main difference right there in our application of Faraday's law to this outer region. That's how it differs from our application in the inner region, this right here. The next term, dt of that phi will be the same as last time. That'll just be equal to ddt of this term here, pi r squared. Pi big R squared is a constant. So this will just depend on the rate of change of the magnitude of the B field inside the solenoid, which ultimately will depend on this current I running through the coiling wire. Change that I, you change that B, you change the flux. Okay, now applying Faraday's law and thinking about the direction of the E field based on Lenz's law. The argument for Faraday's law outside the solenoid is the same as the argument on the inside. We have a magnetic flux pointing out of the page, and if, as in our last example, the magnetic field is getting stronger with time, that is, if I is increasing with time, so B is getting stronger with time, then the flux is increasing with time. We're getting increased magnetic flux out of the page. Lenz's law says that our induced E field will attempt to oppose that. So we'll get an induced E field that tries to put magnetic flux back into the page to oppose that change, to keep the magnetic flux at what it was. So we're going to get, once again, a clockwise E field out here, a clockwise E field that would attempt to drive a clockwise current that would attempt to put magnetic field back into the cage. So we can draw in a clockwise E field vectors at all points on our Faradian loop, just like on the inside. Okay, so then E and ds are anti-parallel at all locations around that path. So we get a minus the closed path integral of the E field strength times ds equals this over here. Our E field will be uniform all the way around that path, so we can pull it out of this integral. And then we add up all the ds's around that path, and we get the circumference of our Faradian loop. 2 pi times little r. That all equals the opposite of the time derivative of the flux, the opposite of this, so minus pi big R squared ddt of the magnetic field strength. And so we conclude that the electric field, the induced electric field outside the solenoid as a function of distance from the center of the solenoid and potentially as a function of time, since this is a function of time right here, it's just equal to 1/2 big R squared over little r. So we've got a 1 over r function, and then times the rate of change of the magnetic field. We've got a 1 over r function, an induced electric field that drops off like 1 over r outside our solenoid. So if we were to graph the electric field, our induced electric field everywhere in the region, from the center of the solenoid to the surface of it and outside, we had a linear E field on the inside and a 1 over r function on the outside. A familiar result we've seen in a variety of circumstances here. This would be our E field at one moment in time. So for some particular moment in time here, this would be our function. And then as this changes with time, the magnitudes here would change in time. This would scale up and down as this went up and down with time. Okay, and then here is a picture of our E field lines everywhere. Here is our, in orange, our copper wire. So we had these looping E field lines on the inside, widely spaced towards the middle where E goes to 0, right at the center, but then getting more densely packed towards the solenoid here. Then on the outside, strongest E field right near the surface of the solenoid, then dropping off, so E field lines getting more and more spaced as we get further and further away. So incredibly, our changing magnetic field inside the coil is going to be generating a looping induced E field everywhere, all the way out to infinity outside our coil. That's electromagnetic induction. Okay, I've got a follow-up. I would like to look at energy conservation in this context. So I've restated our basis for Kirchhoff's law here, modified into Faraday's law by making this a closed path here. So the delta V along a closed path is 0. You end up back where you started, the same V that you started at. That gets us here. But I would just like to kind of, even though this term is 0, move it over to the right-hand side here and to get this statement of Faraday's law with that term still sitting over there. Okay, and now consider some little point charge Q located, say, inside the solenoid or just outside the solenoid. Some point charge Q located maybe here or out here. And suppose it were confined to a wire, like if we stuck an additional wire out here for that point charge to circulate around in, or if we stuck an additional circular loop of wire in here for that point charge to move around in. This looping clockwise E field would exert an electric force that would be speeding up that that charge Q all the way around the loop. speeding it up so that by the time it got back to where it started, it's going faster than when it started, and then it would repeat, speed it up again. That's going even faster, and speed it up again, and going on even faster. And it would continually repeat, it would continually move around this, not in uniform circular motion, but getting faster and faster and faster each time, gaining energy with each completed lap. That's a bit unusual for us. We don't expect electric fields to return a particle to where it started with an energy different from when it started. In other words, we expect electric fields to be conservative. This one doesn't appear to be conservative. Let's investigate. So, okay, here's our statement of Faraday's law here. I would like to note that we can write the electric force on our point charge with this formula, and the work done by that electric force with this formula. So if I multiply this whole thing through by the charge little q, then I have the work done by the electric force in one complete orbit around this path. So we're doing a closed path integral around this path. So the work done by this electric force over one complete orbit equals the opposite of q dt of phi minus q delta v. And that delta v here is still 0, but I'm hanging on to it. Note that this last term here that I've been hanging on to, q delta v, that's the change in electric potential energy. So if the delta v is 0 around this path, then the change in electric potential is 0 around that path. So as the particle speeds around, it ends up back at the same u that it started with, but it's going to be going faster because it got sped up by this E field the whole time. So in our work energy theorem here, EWalk, the total work done is the work done by the electric field and the work done by the magnetic field around that path. Well, the B field cannot do work. We've seen why that is. So the net work done here is just the work done by the electric field. That equals our change in kinetic energy. This electric field speeds the particle up every time it completes another loop. So general conservation of energy here says that the delta k plus delta u over the course of one full orbit equals the work done by non-conservative forces. Well, if delta v is 0, then delta u is 0, and we say that the change in the kinetic energy can only be due to non-conservative forces. But the electric force is changing the kinetic energy. Therefore, the electric force equals delta k equals the work done by non-conservative forces. We're forced to conclude here that this electric force, this induced electric field, and the force that goes along with it is doing non-conservative work. The work done by induced electric fields is non-conservative and, in fact, path dependent. It doesn't just matter where you end and where you started. It matters how you got there, because each complete loop will end you up with a different energy from that with which you started. So, big picture, it's still true that magnetic fields cannot do work, but a changing magnetic field, producing this here, a changing magnetic flux, a changing magnetic field creates an induced electric field that can do work. And that induced electric field, in fact, does non-conservative work. Very different from the electric fields we first encountered. Okay, a little footnote here in case our main conclusion here bothers you. The work only appears to be non-conservative. In fact, it's still true as a general principle that energy can neither be created nor destroyed. So this non-conservative work that the electric field appears to be doing, this energy that's being added or removed by these induced electric fields, that energy is actually being transferred to or from whatever outside system is changing that magnetic field in the first place. So we've been neglecting the part of the system that was changing the magnetic field. That is some reservoir of energy that's transferring energy to and from our system via this seemingly non-conservative work being done by our induced electric